Sehr geehrte Damen und Herren, herzlich willkommen zu unserem ersten Webinar. Es freut mich sehr, dass Sie heute dabei sind. Mein Name ist Lukas Sebi, ich bin Geschäftsführer des Nuklearforums Schweiz und es ist mir eine große Freude, Sie zu dieser spannenden Veranstaltung zu begrüßen. Es ist unser erstes Webinar und ich hoffe, es gefällt Ihnen. Heute haben wir die Ehre, Kirsty Gogan, Mitgründerin von Terra Praxis, als Referentin begrüßen zu dürfen. Sie wird uns wertvolle Einblicke zum Thema die KI-Revolution mit Kernenergie vorantreiben geben und uns aufzeigen, wie künstliche Intelligenz und Kernenergie zusammenarbeiten können, um die Energiezukunft nachhaltig zu gestalten. And now I'm happy to introduce Kirsty. Kirsty is an international recognized strategy consultant for governments, industry, and NGOs in the field of innovation and competitiveness in nuclear energy. She's the co-founder of Terra Praxis, a non-profit organization promoting advanced nuclear energy for energy security and decarbonization. And she's the managing partner of Lucid Catalyst, an international consulting firm specializing in cost-effective decarbonization strategies. I wish you an engaging and informative session, and now I'm happy to give the floor to Kirsty.
Wonderful. It's my pleasure to be here, and thank you so much, everybody, for joining. So I have a short presentation just to share some of the thinking that we've been doing around this topic, and I hope that we'll have time then for some discussion as well during this webinar. Well, thank you very much for the kind introduction. Yes, I'm the co-founder of two organizations, Lucid Catalyst, which is a consulting firm, and then Terra Praxis, which is our non-profit organization. And that's mostly what I'll be telling you about today, the work that we've been doing through Terra Praxis. For those of you that don't know, Terra, of course, means earth, and praxis means putting theory into action. So really, Terra Praxis is about sort of action for earth. And our sort of organization is focused on the sort of twin goals of enabling universal access to affordable, reliable, and clean energy, that also, empowers people and protects nature. And we're entirely funded by philanthropy, and we're focused really on developing sort of innovations and accelerating scalable, equitable solutions to decarbonize the largest sources of global carbon emissions. We have a very special interest in nuclear energy, partly because we think it's been quite neglected as a very interesting solution with that potentially very significant impact in enabling these objectives. And also because, because of neglect and impact, essentially, it's been neglected and it could be very impactful, but the way that nuclear energy is delivered today cannot really achieve the sort of costs and the speed and the scale of deployments that are needed for a very broad range of use cases, which is some of and so these are some of the topics that I'll be focusing on today. We have also a sort of an important principle that informs our work, which is that, given the sort of scale and urgency of the need to not only radically reduce our emissions from burning fossil fuels, but also enable energy access to billions of people today that currently lack access to energy, we don't really have time to build everything new. And so one of the kind of key organizing principles in our work is figuring out ways in which we can repurpose existing fossil-based infrastructure to enable continued operation without emissions. In that way, protecting nature whilst also sustaining those jobs and the associated economic and social benefits. So let me give you a couple of quick examples to sort of bring this to life. We've been working with the US government, for example, for many years, and the DOE, the Department of Energy, recently identified 145 retired or retiring coal plants that could be repurposed with new small modular reactors So in other words, co-locating small modular reactors with those existing coal plants, potentially providing a new heat island that could enable the continued use of the existing power island, the turbines, or just co-locating a new power plant with an SMR and then reusing the transmission. In that way, sustaining the jobs, sustaining the economic benefits associated with the continued operation of those plants, and also, of course, reusing the transmission. Now, the DOE found 174 gigawatts of new nuclear potential at those 145 coal plants. And on average, those coal plants are operating at about a 50% capacity factor, which means that if you were to repurpose those coal plants with nuclear operating at, say, a 90% capacity factor, that would almost double the amount of energy going into that existing grid network and, of course, without emissions. So repurposing coal plants is a very interesting opportunity and is actually attracting a lot of bipartisan political support, because a lot of these coal plants tend to be in areas that are, Republican areas, for example, and those communities are facing currently an uncertain future. The other example I would like to share with you, just to sort of put this into context in terms of the scale of deployment that we should be really designing for, is a group of oil and gas companies, also in the US, that were interested in decarbonizing their upstream operations. And this group of oil and gas companies identified 3 use cases that couldn't easily be decarbonized through connection to the grid or with wind and solar, for example. And these 3 use cases were drilling, compression, and fracking. And these companies identified 50 gigawatts of existing engines and turbines operating today that they would be interested in decarbonizing with microreactors. Now, these are use cases that are very small. These are, 1 to 5 megawatts in scale. So this is potentially a market for 5,000 to 10,000 microreactors just in North America, just to serve those 3 use cases. So I think often when we talk about the future prospects for nuclear energy, we are at risk of really underestimating the scale of our existing energy infrastructure that we could be repurposing to continue operation without emissions. And because we're not fully, thinking through the scale of this existing energy infrastructure that we should be reusing, we're not necessarily designing strategies that can enable the real scale that would be needed. So let's think a bit more about the scale. So this is the current global energy outlook. This is actually an optimistic trajectory. It's from the stated policy scenario from the International Energy Agency. This one's actually from 2022. And you can see here that the projections suggest that by 2050, the majority of our energy will still come from fossil fuels. And that's very consistent across all mainstream energy systems scenarios. And that's partly because we're not able to fully decarbonize the vast majority of our current fossil-based energy beyond the power sector, especially. And it's also, of course, because global energy demand is continuing to rise. So the deployments of clean energy, frankly, cannot keep up with the demand growth. Now, if we did want everybody on the planet to have access to OECD average levels of global energy access, you can see that red line on the chart here with 84 written over it. That's roughly the sort of average of global energy access. It's a kind of equivalent to, say, the Czech Republic, for example. If we wanted everybody on the planet to have modern living standards equivalent to what is currently enjoyed in the Czech Republic, then we would need an additional 30 terawatts of power. So not only do we have to fully decarbonize our global energy infrastructure, but we actually also probably have to double or triple it to meet rising global demand by 2050. So this is the future we want. So here you can see a radical increase in overall deployed energy, and you can also see that our existing fossil infrastructure, the coal and the oil and the gas, is being repurposed to enable continued operation without emissions. So the rest of my talk here is going to be about how we might do that. How do we get there? How do we get ready between now and 2030 to start that deployment, massive deployment of clean energy, 10 terawatts in 10 years, starting in 2030? Well, we can't do it with traditional construction projects. I'm sure everyone here knows that traditional construction in nuclear energy, but also more generally, is expensive and complicated and slow. Essentially, you're building these plants by hand. So sometimes, at an event like this, I might make a sort of little survey of you all and ask, hands up, who thinks A is a product, or who thinks B is a product? And I'm going to tell you the answer is A is a product. This is a product which is made in a factory. So let's just unpack that a little bit. So the first thing to say is that products are engineered for factories. For example, this is a sort of gigafactory. It's actually a Tesla gigafactory, which is extremely unfashionable now, of course. It took about 5 years to build this gigafactory from construction start to full production. It's making 500,000 vehicles per year, 20,000 employees. It has about $30 billion in annual revenue per factory, and its energy output is equivalent to about 250 kilowatts per car. So that's a production of 125,000 megawatts per year. And that means that for each of those 20,000 employees, they're each producing about 5,000 kilowatts per worker per year at a cost of about $240 a kilowatt. So let's compare that with our, best case, most successful recent nuclear new build project, which was 5,600 megawatts, took 10 years to build, cost 24 billion, has about 5,000 workers, making about 560 megawatts per year. And that's 112 kilowatts per worker per year at a cost of $4,200 a kilowatt. Now, let me just compare and contrast here. This is the kind of difference that we need to accelerate deployment by 100 times to start achieving the sort of scale of production that I opened this discussion with a moment ago. The basic stats are that the gigafactory is producing about 223 times more energy than this very successful nuclear construction was able to produce, producing about 45 times more energy per worker per year for 18 times less of the cost. So this is sort of an important detail that's bringing me to the next sort of part of our discussion, which is how might moving from project-based construction projects to high volume manufactured product approaches enable a really different way of thinking about how we license, how we design, and how we ultimately automate the production of nuclear products to enable the kind of scale of production that we might see in other industries, such as the automotive industry. How do we close that gap? This slide is just before we step into the sort of strategies that enable that product-based approach. For anybody who's sort of wondering whether we might not need nuclear because, solar is very cheap, solar is already a commodity, and we're already manufacturing at scale. Solar is wonderful, and it will have a very important role to play in our future energy system, but it's not really a one-size-fits-all situation. And this is just one example to sort of illustrate how solar may not necessarily be the right fit to replace the output from coal plants. So here you have an example of a coal plant in the UK. It's about 1.5 gigawatts operated. It's closed now, operated at about 90% capacity factor. If you wanted to replace that 1.5 gigawatts, 90% capacity factor with solar and batteries, we've assumed a very low cost for solar of $1 a watt, and we've given a reasonably generous capacity factor of 18%. Actually, in the UK, really, it's more like 9%, to be honest, but averaged out, so 2.7% capacity in winter, 18.7% in summer. You can see here that the size of the the solar farm you'd have to build to accommodate those winter months is 35.6 kilometers on one side of a square. Just think how long it would take you to walk 35.5 kilometers, and that's just one side of a square. So, and then of course the scale of the build is so large that even with a very low assumption for solar, it actually starts to represent billions of dollars of investment that would be needed, in this case between 15 and 29 billion dollars, just to replace the output from one coal plant. Or you could co-locate your new extremely dense and reliable and high capacity factor and emissions-free heat box, as we would like to call it, a mass manufactured reactor at an existing coal plant site. Here you can see an illustration of a coal plant with a new heat island co-located with the former coal plants, and data centers are being built next door. And this heat island is supplying heat to these thermal energy storage tanks, which then make steam that can be run through the existing coal plant power turbine to enable that coal plant to keep operating just like it did before, but without having to burn coal. And to enable that sort of heat box deployment, we are looking at a highly manufactured deployment system. Here you can see the orange box is the heat box, the manufactured reactor being installed in a manufactured cocoon, providing all of the shielding and impact protection that would otherwise typically be provided by a complicated civil structure. Now, when we started working on these strategies, we attracted the interest of a big company that you may have heard of called Microsoft. And Microsoft have quite an interesting values alignment in terms of their goals around the trilemma. So expanding access to clean, affordable energy globally, to serve their customers as well as to decarbonize their own operations. And here we are signing a strategic framework agreement with the president and chairman of the company, Brad Smith, who really liked the idea of being able to repurpose former coal plants to enable, the socioeconomic benefits to be retained, and using the existing transmission and enabling, continued supply of reliable energy, upon which, of course, all their services depend. And we started that relationship in 2022, and Microsoft not only sort of provides, technology advocacy and policy support, but they're also bringing their skills and capabilities to this. And so with Microsoft, we've you can see a Wall Street Journal article here about one of the projects that we've been working on with them, which is developing AI solutions to accelerate deployments of nuclear energy. And that's as part of our sort of Repower consortium. So it started with Microsoft. We're now working with a whole range of different organizations from across the whole of the delivery ecosystem. And many of these companies are interested in leveraging the AI solutions that we're developing, and also bringing their own skills and expertise to support this broader objective to deploy fast, low-cost, and repeatable solutions for repurposing coal plants and other energy infrastructure. As through the Repower Consortium, we've identified 5 key actions that would be needed between now and 2030 to enable that massive, increase in deployment of nuclear that could support full decarbonisation and universal energy access from the chart that I showed you at the beginning. Just 5 simple actions. Doesn't sound too difficult, does it? So the first thing is moving into a manufactured delivery model, both for the reactors themselves as well as for the deployment architecture. These 2 things combined enable a really radically different approach to product-based licensing, and then that de-risks the schedule and the cost for customers, enabling customers to sign PPAs, all of which ultimately then will be very attractive to project developers, as essentially what you're looking at is the commodification of the delivery of nuclear energy, much like we've seen in the commodification of solar and other renewable technologies. So we're working on strategies to enable these 5 key actions to be implemented, and we're making progress across all 5. But today I want to spend a little bit of time, particularly on licensing and how we could use AI in particular to accelerate licensing. So this is now some content that we've jointly developed with Microsoft to sort of explain the benefits and the progress that we've made on developing a Gen AI for nuclear licensing solution accelerator. Because of course everybody thinks about AI as a huge, energy hungry technology, which indeed it is, especially when you're training the AI. I think AI is currently using about 1 to 2% of our total global energy, and that is projected to increase to anything up to 30% in future. We'll see. It's a dynamic situation in terms of what the future energy demand of AI will be, but there's no question that as a civilization, as a global civilization, our energy demand is highly likely to continue growing. And that's for a very broad range of large industrial applications, not just from the global technology companies, from the hyperscalers. But there's a flip side to this. Not only is AI a user of energy, what's very interesting is how we might be able to leverage AI to actually accelerate the deployments of more clean energy infrastructure. So this is a sort of snapshot from the tool that we've developed, and I'm going to step through it in a bit of detail. I know this is a very busy slide. Excuse me 1 second. But essentially what you have here is starting with training the AI on the licensing regime, generating a sort of database of all of the training materials, then generating documents, and then there's a process of iteration and engagement around the documents that are generated. Obviously, there's a lot of integration against tens of thousands of pages of documentation, which can then be submitted ultimately to the regulator. And interestingly, we're also working with regulators who are interested in using AI, to support the reviews that they're doing of these license applications as well. So just to kind of go into a bit more detail, so it's not just sort of historic licensing data that the AI needs. For hazards, for example, such as floods and earthquake history, you'd have to make relative real-time data sets available, geographical data, seismic data. That all gets sort of fed into the generative AI tool, along with all of the sort of expectations and standards and codes and so on associated with the licensing requirements in the region that you're developing your license application for, specific to the site that you're developing your application for. And then the model leverages plugins to automatically pull in all of that data to support the write-up of the handling of the hazards for the license application. The AI can then generate entire documents, again, using sort of previous licensing data, project specific data, company data sets, all gets plugged into the licensing workflow to be ready for human review and refinement. And what's very interesting, I think, is that, not only can you rapidly produce compliant applications with real data, in some really quite large data sets, as you'd expect, but you're also radically reducing the sort of overall manual labor required in that application production process, because as the AI makes updates and amendments in some parts of the document, the AI will relentlessly check for consistency and quality and compliance across all of the documents in the associated application. And that's actually one of the big tasks that today we're paying very expensive professionals to do on a manual basis, and instead using the AI we can automate a lot of that process, and then have the human professionals spend much more of their time on really adding value. So I think this general productivity improvement is really key, and this actually is going to really be a real benefit, I think, for the regulators themselves. Right now it takes 6 months just to dock it, just to receive an application and confirm that it's compliant. So leveraging AI, even just to do the initial quality check and compliance check, I think is going to make a really big difference. Now, this really matters because today it takes, between $50 and $100 million to submit, for example, an early site permit for one site. This tool, we'd expect, will not only reduce that cost radically from to a fraction of what it costs today. It also reduces, of course, the time associated with generating that license application. It also reduces the complexity and uncertainty associated with making that big upfront investment that you have to make today with an uncertain outcome, requiring huge capital investment before you even know that you have a project, and years of work long before you'd ever be generating any revenue. So the reason that we're very interested in this particular application for AI is because this potentially can reduce one of the major barriers to getting projects started. Now, the latest version of this tool can actually generate early site permits for fleets of sites. So, the next step for us would be to generate early site permits, maybe for 100 sites, 100 former coal plant sites. And so that example that I started with at the beginning of this session, the 145 retired coal plant sites that could have 174 gigawatts of new nuclear just in the United States, one of the reasons that we would find it difficult to operationalize that opportunity today is because these are not licensed sites. So if we can leverage AI to leverage all of those sites, just think what a radical difference that could make to supply chains, for investors, for technology developers. It would make this abundance of licensed sites available, which could enable real investments in the rest of the manufacturing supply chains and other aspects of the system that are needed to achieve that real transition from a one-at-a-time construction-based approach through to actually being in the gigafactory production scale that's needed if we're serious about meeting our climate and energy goals. So here are again, just to remind you before I close here, the 5 enabling conditions. We're working on all of them, but you can see how product-based licensing accelerated by AI, or even just leveraging AI to make sites licensed today, could help to unlock these other key enabling conditions. And I think that is all I have, and I hope that I'm sort of within time, and I'm very grateful for your attention and looking forward to questions and discussion. Thank you.
Thank you very much. Thanks, Kirsty, for this great presentation. I learned a lot. Thank you all for attending our first webinar. We hope you got interesting insights from this session. Our next event is already scheduled for June 23rd, when we will host another exciting webinar with NAGRA. That's the National Cooperative for the Disposal of Radioactive Waste. And they will tell you where do we stand in Switzerland regarding the radioactive waste. So we would be delighted to have you on board again. We wish you a wonderful day and look forward to see you here again. Bye-bye.